So welcome to Lecture 11 of CSCI 5828, Foundations of Software Engineering. So this means we're starting week 6. By the end of this week on Sunday, sometime on Sunday, I need you to send me your first presentation. It's due on that first day. And what I'm going to do is this week I'll create a Google Doc and put that up so that you can go into the Google Doc and say, my team name is, my title is, and the link to the presentation from there. Yes?
Is there any way we could push the due date for the homework to Thursday so we can finish the PowerPoints and concentrate on that, or the presentation?
The homework is due next week on Tuesday.
No, I know that, but I just thought since, the due dates are so close, like having to work on the homework and the presentations at the same time.
Okay. I'll think about it, but I need to probably squeeze in one more thing before the midterm so that we have the ability to work on it, and so I'm running up against that as well.
Okay.
And I'm hoping that the work on the presentation isn't all pushed till Sunday. So keep working on the presentation now and clear up your weekend for the homework as best as possible. Yes?
Since you're out of town the week prior to the midterm for Grace Hopper and everything, will you be putting out a midterm review or anything?
Yes. So actually, yes. So question is, will I be doing a midterm review? So the answer is yes. And when I do that is typically the lecture right before the midterm. But of course, that is the lecture that I'll be gone on a trip that week to Grace Hopper. So what I'm planning on doing is I'm going to be contacting Kate today to find out when I can come into this room or one of their other studios and pre-tape the 2 extra lectures that I have to give, because I've got the 2 lectures this week and then 4 lectures to give. The 2 for next week while I'll still be here, and then I'll have to do an additional 2 next week for the week after that when I'll be gone. So once I've locked down with them when I can do those extra lectures, I will advertise those times. So if anyone can attend and you would like to attend, then please come to those extra sessions. And then what I do for that midterm review lecture typically is I tell students to come with questions. And of course, not all of you will be here this time. So you can, of course, send me email on questions you might have. But I do a whole overview of what we covered. I remind students of what was on the homework assignments. I discuss through some of the more interesting things that I'll know will be on the test. And so that session really is me kind of giving an overview and then typically asking students for questions and then responding to those questions. So what I'll do instead is I'll have, if students send me questions ahead of time about things they'd like to know, then I will have a session, I'll have a section in that lecture where I will respond to those questions. And so that's the best I'll be able to do. There'll be four lectures for me next week, and the 2 extra lectures, I don't have any control over when those times will be. I just have to get into the studio to get them recorded. So that's what we're going to be doing. And as an overview, this week I'm planning on getting into the closure material that's on chapter 3 of our textbook, the concurrency textbook, and get as much of that as I can today and tomorrow, and then, today and on Thursday. And then next week I'm going to start a series of lectures on the Agile portion of our class, looking at the other textbook, the what is it called? I'm blanking on the name of the textbook. Just a second, I was just looking at it today. The nature of software development. So we'll be having 2 lectures on at least 2 lectures on that, and then 1 lecture from a previous instance of this class on some more Agile information that I want you to know before the midterm. So that's the current plan. 2 more concurrency lectures this week. Then next week, 2 lectures on the Agile textbook. The week after is the week I'll be gone, but the pre-recorded lectures will wrap up the Agile material and then have a midterm review session. And then the week I come back, which will be week 9, this is week 6. On week 9, on Tuesday will be the actual midterm. Yes?
I just have one more question about the midterm. Is closed book or open book?
It'll be closed book. Okay. So let's get started, and we've got a bunch of stuff to cover today. And in particular, we had gotten to this portion of the lecture slides on Thursday for Lecture 10, which was looking at this producer-consumer example. Just as a reminder, at a high level, what it does is we've downloaded a file from Wikipedia, which contains all of the contents of all their articles generated just a couple weeks ago. It's how big of a file is it again? It is 51 gigabytes in size when you expand it, and there it is. You can always do a head on this file to see the start of it. As you can see, it's just an XML file, and you can see the tail of it, and there it is, closing off that XML file, a closed page tag and a closed MediaWiki tag. And in between that is 51 gigabytes of text and you know, lots and lots of data. I'm actually running on a machine right now where I could probably load that into memory, but it would take a while. So I won't try to do that. And at a high level, the program is going to parse the first 100,000 pages that it finds. And so this right here, when I say pages, I just mean page tags in the XML. There's an open page and then a closed page. And so we will go and find the first 100,000 of those pages, and then basically split them on word boundaries, and then count up all the words and keep track of every individual word. So there's going to be a hash table that we have where the key is the string, either the word or the punctuation mark or whatever it is, and the value is the number of times we've seen it in those first 100,000 pages. And then I have modified the code that came with the textbook. In particular, if you look at the code that comes with the textbook, in the code that he has deployed, it basically has this code that you can see right now. There's a call to keep track of the start time. There's this call here which tells the pages class, go parse on demand the first 100,000 pages of this file. Then we loop through the file, and this is where we call this count words method, passing in the current word that we've got. And that count word method, I'll show at the bottom, is just a method that manipulates this hash map up here, which is strings to integers, called counts, just a regular old hash map. And we just keep looping through that. So the high-level code is very, very succinct, and it does exactly what you would suspect. The code that gets deployed in the book then takes the end time, as you can see here, and then I think prints out a message. I can't even remember if it prints out a message, but it'll print out a message saying that it's now done. And what I did was I then modified that, because actually now that I remember, when I first ran this program, it didn't do anything for 3 minutes and then came back to the prompt. The code that gets deployed actually doesn't print anything out. It just counts the pages and returns to the command prompt. So I modified it so that we could print out, when is parsing done? That's the key thing we want to focus on. And then I added a bunch of code here that right now we end with strings to integers, words to counts. This code here that I'm not going to step my way through swaps that, creates a new hash table in which you have integers to all the words that had that count. And then I have a thing down here where I think I sort it. Yeah, here I call descending key set, which then sorts the integers from biggest to smallest. And then I print out the top 25 terms. So that's what the code I did added to this. And I'm kind of in a bind because the licensing agreement that ships with this book doesn't allow me to distribute this code. But I can it'd probably be okay for me to distribute the small part that I wrote on my own and say, insert this into your main file so you can see this on your own machine if you want to run it at home. But that's all that does. So at the very end, we can see that, in fact, we are parsing all these words. Now, I'm not going to run this first one, which is just the single-threaded implementation, because it takes about 2.69 minutes to do so. But that's going to be our baseline, 2.6 minutes, just under 3 minutes to parse that file for the first 100,000 pages. And now what we're going to do, what the book looks like at the end of Chapter 2, is different ways we could make this parallel, because the first version is just a single-threaded solution. So the first attempt to make it parallel is to do what's called a producer-consumer architecture. So you're going to have a pool of threads that are readers and are going to be reading the XML file. And they're going to be, as they finish a page, they're going to stick it onto a queue. And then that queue is going to hold the pages until another pool of threads called consumers can pull those pages off of the thread, do their count, update the total counts, and then keep doing that until there are no pages left to be parsed. And what we're going to do is put onto the queue at the very end the producer thread, once it's realized that it's done with parsing all the pages it needs to do. It's going to create what's called a poison pill, which is basically just a special object which says, hey, producer is done. So there'll be no more pages after this one. And so that simplifies the coding of the consumer. You can just loop until you get the poison pill, and then as soon as you see that, you quit and you're done. So the difference here, and I think in this first particular implementation, they actually only have one consumer and one producer. Let me remind myself about that. So what we're going to do is look at word count producer consumer, which comes from the book. And again, the only modifications I've been doing is with the main file just to make it produce more output. But what we want to look at now is, let's look at word count to see how they set it up. So here what they do is they create an array blocking queue. So this comes from the Java util concurrent library. And what it does is if you ask the queue for the next element and there's no element, it blocks the thread that's asking for that element. And so you can have your consumer thread spin up and immediately try to pull from the queue and block, and then it will just wait until the producer starts putting stuff into the queue. And as soon as the producer puts stuff into the queue, it does the condition variable that we saw last time, and it signals the consumers to wake up because the queue is now not empty, and the consumers will wake up and they'll start pulling things off. Now, I say consumers and producers, but what this particular implementation does is one thread for the counter. So there's one wait a second, counter, new counter, queue, counts. Thread parser. Oh, right. Yeah. So the counter is our consumer. So here we are creating a new counter, which the counter is our consumer in this case. We're passing in the queue, and we're passing in a reference to the hash table that needs to be filled by the end of the program. And then we're creating a parser thread, which is our producer, and the producer just gets handed the same instance of the queue. So between the consumer and the producer, they share this queue. And then we tell the consumer thread to start up. Then we tell the parser thread to start. We join that parser thread. Here, once we've joined the parser, we know the parser is done. So now we put the poison pill into the queue right here. Queue.put new poison pill. And then we print out and we say we're done with the parsing, and then the rest of the code kicks in to print the rest of that stuff. So now this still takes a couple of minutes, even though there is some concurrency going on here. But so let me just get that running, and I'll talk through some other things while we wait for it to finish. So what we're going to do here is say maven exec :Java. And then over here, if I go back to that same machine and then run the top command, you'll see up here towards the top of the thing, eventually this Java command kicks in right here. And this is where we can monitor the CPU usage of this solution. And as you can see, this is on a machine that has a ton of cores, I think 16 at least. And right now it's it's actually, it might even be done. Let's see. Parsing complete. Okay, actually, weird. Okay, so this was done in 30 seconds. Something's wrong. Because it should be 2.45 minutes, not 31 seconds. Did I do the right one? That's bizarre. It didn't print out. Okay, let me. That is, okay, something weird's going on. What did I do wrong here? 100. Go look at the parser. Because that's what we expect at the end once we've done all the changes. Okay, wrong one. Parser, producer, what's it called? Parser. Nope, Still doing 10 million pages, or 100,000 pages. And then it didn't print out the dictionary at the end. Version complete. Print out the term. Where's my print statement? So print out the index, print out the term. Okay, yeah, so that was there. Something came up empty. All right, what happened there? My apologies. So I was trying to figure this out. So, oh nope, and it went up and got the right file, .. word count and wiki. All right, that is bizarre. And that again. 30 seconds, that's just too fast for what I saw this weekend. So 100%, so what I was trying to say was that even though we had 2 threads, CPU utilization here is only at 100%. And so we're only getting a single-threaded solution's worth of work out of it, but it's done. I don't get it. This was taking 2 minutes during the weekend. I don't understand it. Let me just run again here. On this one, this is the single-threaded version. And here, the single-threaded version, no surprise, is that, oh, see, all sorts of different behavior. So roughly at 100%, but sometimes higher, so no way to explain that. But mainly at 100%, which is what you would expect. And now this one is actually taking the time I thought it would. Well, unfortunately, I do not have the time to debug why that one is going so fast. Let me just keep going on. This weekend, when I looked at it, I was seeing 2.45 minutes per run, and the CPU utilization was, as we had seen, about 112%. So there was some separation of work, but not by much. But I have to say I'm really stunned by the fact that it finished in 30 seconds. Okay, and I didn't show it. I'm not going to do this now, but I've done. I was playing around with it, changing the queue size to see if the queue size would make things go faster. And this past weekend, the impact was minimal. You wouldn't see much of a change, even though the queue size was bigger. And the problem there is that the time it takes to parse these files individually is actually very small. If you take the consumer and turn it off so that it pulls pages off the queue but doesn't count them, the whole program takes about 18 seconds to run, and that's with the parser parsing just the time it takes to parse the 100,000 pages. So changing the size of the queue is not going to impact the speed of the program. Because all of the time to parse, or all the time that's being consumed by this particular program is in the counting done by the consumers. So as you can see now here, we're getting a more typical execution time. So I'm actually just stunned that the other one executed so quickly. Anyway, so let's get back into the swing of things here. So what we're going to do instead now is to create multiple counters. The first solution we saw only had a single counter. And those counters are going to share the counts hash table among them. And as they pull a page off and finish the counting, they will update counts. And so you'll expect, if we go back to our discussion of contention, we'll see that these counter objects are going to need to somehow synchronize their access to the counts hash table. Okay, so, and I think I've already looked at this. So we need to create multiple consumers, have them work together to pull pages off the queue and count the words in parallel. The problem here is that we will have a shared resource between the consumers, which is this hash table. And we will protect the hash table with a static lock that's shared by all consumers. All right, so now let's take a look at this. So this one finished now in, yeah, there's my code to print stuff out. And this one finished 2.7 minutes. So that's what I was expecting the other one to do. But let's go ahead and look at the one I want is the word count synchronized hash map. All right, so target, not target, source. So in this one here, the setup is now the same. So we go to word count. There's a constant here which defines the number of consumers, in this case just 2 consumers. And now we're going to be using an executive service to create those counters and add them into the thread pool. So here we're saying executor.execute, and the executor wants runnables, which is what counter is. So we pass counter into executor, and they'll run the consumers for us. Our parser is created the same way. And so in this way, we set up the same thing now, but with just 2 consumers. So the only thing that changes then is our consumer code. And the big thing here is that we've got this access to a map called counts right there. And what we got to do is make sure that if one consumer is updating counts, the other consumer can't update the counts. And so we do our counts right here in a loop. So as we get our page, we loop through word by word, and we call this count word function. And here we use a reentrant lock, where we say lock.lock. Then we do now that we've got the lock, we can go and do the code that updates the word count for counts. And then in the finally block, we unlock the lock. So the 2 consumers will take turns updating the hash table word for word. So let me just see here if I can say Maven. I'm going to start over here. So Maven clean, and then Maven-Q compile, and Maven-Q exect Java. So now that it's running, we'll see over here, Java comes back. We've got two threads now, and so in general, or we've got 3 threads. We have the producer, and then we have the 2 consumers. And so in general, you'll see the CPU up closer to 200%. Even though there's 3 threads that are active, combined, their work is consuming about 200% of the CPU resources. And so we're getting some parallelism, more parallelism, but in this case, I won't necessarily let this run the whole time. Oh yeah, actually here I was having it print out how many pages it still had to go. I was just trying to monitor things. So it's parsed about 8,000 pages so far, and it's still got 91,000, 90,000 pages to go. So actually in this particular implementation, we actually made things worse by that contention around the lock. Each consumer thread has to say, oh, I've got a new word. Let me add it to the hash table. I need the lock again. And they're going to spend most of their time now fighting for that lock and not getting much work done. So what they do is they say, well, there's a special purpose hash table in Java util.concurrent called the concurrent hash map. And maybe that'll do the trick, because it is explicitly designed to allow us to have multiple threads update the map without having to do synchronization or locks on it. The hash map does synchronization internally. So this data structure tries to allow parallel reads and writes on the hash table without having to do explicit locking. So to do this, however, in the presence of multiple threads, you have to adopt a different style of use. So when you go and look at concurrent hash map and look at its API, it has a different API. You're used to, most hash tables are put and get, and that's basically it. Those are the 2 primary ones. With a concurrent hash map, you have put if absent and replace rather than put. And so what happens here in the presence of multiple threads, if you read from the hash table, So you say, hey, I'm going to update, I've seen the word the, I want to update its count. So you ask the concurrent hash map, hey, give me the count for the word the. It'll come back and say, okay, it's 100,000 instances so far. So you're like, great, I want to make that 100,001. So you call with replace, and you say, hey, you told me the value was 100,000. I want the new value to be 100,001, and here is the key that we're talking about, in this case, the string the. Now, replace can fail. It can say, oh, the value is no longer 100,000. While you were looking at the value 100,000 and deciding what to do with it, some other thread came in and changed it out from underneath you. And so replace requires you to say, here's what the old value was, here's what my new value is. It only gets committed if your old value matches the correct current value. So the code for this now looks like this. When we're counting a word, we go into a true loop, so an infinite loop, and we say, give me the current count of the word. And then if current count is null, then we're going to say, okay, if counts dot, what we're going to do is say, okay, well, here we have a brand new word, so here's the word, put if absent, and the value should be, the initial value should be 1. And what we need that to be, if we call it this way, is for it to return null on that call. If it returns anything else but null, then we know some other thread beat us to it. So while we were trying to put the initial value in, some other thread activated, got in, put the word in, and was done, all between us getting this word and then trying to put it. So if that happens, then you can't put the, you're not done yet. You need to update still. So you loop back around, and this time you'll get back the value 1 or 2 or whatever it is, and now you're going to try to do the replace. And so here you see is the replace. I've got the word, here's what I think the current count is, and here's what my new value should be. And so you keep looping until one of these returns true, or evaluates to true, and if that happens, then you break out of it. So you have to do this because otherwise you'll get race conditions while you read and then try to write without it. All right, and as you can see here, it's starting to speed up a little bit, but we're not going to wait for it to end. All right, so that version of the one that uses the concurrent hash map is here. Oops. Here. And the big change comes in, it should be set up the same way. So in word count, it's got, in this case, it's got 3 consumer threads. And then the code just loops through and adds 3 of those to the executor. But the change comes in the counter itself, the consumer code itself. And in particular, it gets handed a concurrent map now, rather than a regular hash map. And then down here at the bottom for count word is the code we just stepped through where it has to loop. So there's 3 of these consumers. They're all pulling words off in parallel. As soon as they find a word, they're going to go try to update this concurrent hash map. And we're hoping that that is a little bit faster and that the concurrent hash map somehow can handle more concurrency. Like, for instance, if the 3 consumers all say put on different words at the same time, it can allow all 3 of those to happen in parallel, and no one has to be blocked. It's only if 2 consumers come in and both ask for the same word that you could get some contention. But you can get more concurrency than you could with the lock put around the access to the counts. All right, so in this one, we're going to, again, clean this out and start over. And compile. And run. And I don't know if I had that print line statement in all of them. We'll see. So let's make sure it's running here. So now it's running, and we can see we're at up to about 300% CPU. 304%. We're not seeing close to 400. My guess is because the producer probably can fill up 100 slots in the queue pretty quickly, and then it has to wait. And then once the queue goes under 100, it can add some more into the queue. And so we're not seeing true parallelism from it. We would have to have an unbounded queue where it could just keep putting pages on. Then you'd have to make sure that you have enough memory. But anyway, that is spinning now at about 300%. So for most part, the consumers are able to run in parallel. And just in the interest of time, This weekend, what I saw was the following type of performance. So for 2 consumers, it went down to about 3 minutes with 210%. 3 was 2.86. 4 consumers, it was 3 minutes. And 8 consumers, it was 4.87 minutes. So here, with 8 consumers, 8 threads trying to update the concurrent hash map, we still ran into contention issues. They were spending most of that time, so it was slower than the single-threaded version, right? Almost all of these were slower than the single-threaded version. And that's because there's still contention happening around that map. And so just being able to get work out onto multiple threads is no guarantee of better performance. You've got to make sure that the threads can run in parallel and not interfere with each other. As soon as there's contention, you get slowdowns, because you've been adding in all this sort of stuff to all this overhead to the program. As I said here, what we're seeing is LiveLock in action. I mentioned LiveLock in a previous lecture, and that's where none of the threads are deadlocked. They're all working, they're all making progress, but not a lot of work is happening, right? And that's because they're mostly doing a dance around locks to try and get this thing to work. All right, so we won't even let this one finish because we know it's going to take even longer than the single-threaded version. Okay, so then we're going to go to the final approach that they talk about in the book, which is to say, hey, we're having the consumers fight for the lock on that hash table for every word. Every time I pull a new word off, I'm turning to the hash table to update the hash table. Well, no wonder there's so much contention. Have you seen those Wikipedia articles? There's tons of words in there, right? So every word is involving a contention issue in this thing. What we need to be able to do is to really let the consumers not step on each other's toes at all until it's finally time to update the global map. So the final solution is to have each consumer thread maintain its own count separate from all other threads. And then for that, you can use a regular hash table because only that thread is going to be updating that particular hash table. No need for locks, just one hash table per consumer. And then when the consumer is finally done, you have a concurrent hash map that's global to all of them. And then finally, as they're merging their hash tables into it, you might see some contention. But now that contention is pushed all the way to the end of the program. Right? Otherwise, throughout the majority of the program, that we can run without any contention. This weekend, when I was doing 2 consumers, it went from 2.6 minutes, right, roughly, for that single-threaded version, down to 77 seconds in that first one. Then 3 consumers, 53 seconds, 42 seconds, 24 seconds with 8 consumers. And let's see if we can get that. So the 8-thread version here, where they can run in parallel, was about 9 times faster than the single-threaded version. So to show this, let's clean this out. So clean and compile. And I should have checked to see where I'd left it. I might have to compile again here. So I want to go to, in this case, word count. And this was on 2 threads, so let's just show the 8-thread one in action. So compile this again. And now, here with 22 seconds, do this exec Java, and then I'll show you the code real quick. Over here, we can see when it pops up, that CPU utilization. Yeah, there we go, 880% at that point, 962%. So finally, the consumers are running wild and free with that, no one's bothering them finally. 1,000% CPU, 943 roughly. And at some point, this will finish. And yeah, there we go, parsing complete in this case, 25 seconds. So made a big difference in terms of that single-threaded version. I'm going to have to go back and figure out why that initial concurrent one showed up as 30 today. It's stunning. But this is where we finally see some concurrency. We still have only one producer because we figured out via performance calculations that it just takes about 18 seconds to plow through the 100,000 articles anyway, and there's really no, you could try to make that faster, but you're talking about really diminishing returns. If it's already 18 seconds in a program that takes several minutes to run, you're not going to get your biggest gains there. So you have to find a way to make the counting faster. So we tried multiple consumers. There was lots of contention. We had to keep iterating until we found a solution in which the consumers could largely work independently and put all the contention that was going to happen at the end. So what I want you to do is to really spend some time in this chapter, make sure you understand these different designs. And I'll go back to the drawing board and try to figure out why I got that weird result that put me off my game there for a minute, and figure out what was going on with that. But make sure you understand those different strategies. We're going to see in the Clojure lectures a return back where we see similar performance on word count in using its way to express the problem, and having to adopt similar solutions where we try to get the consumer threads working independently of each other in order to see the same sort of speed up. Okay, and then just as a heads up, I'll come back to Java util.concurrent later in the semester because there's still way more to see in that library. Futures, the countdown latch, and the cyclic barrier, and especially the fork join pool, which is a really cool executor that they have, which can figure out that you've given this thread this task to do, or a task to do something, and the executor can figure out that, oh, that task is going to be blocked for a while, so I'm going to take its thread away from it and have it go work on other work. And once it becomes unblocked, we'll give it back its thread. But we don't have to assign it a thread and then just let that be permanent until the task is done. We can actually steal the thread from it. Yes, question?
You said that you thought there were 16 cores on this machine you're running on.
Yeah.
So if you increase the number of consumers to like 17, would you see any difference between 16 and 17? As you in these types of programs, as you continue to add additional threads, you will get diminishing returns. Your performance curve, whatever it is that you use to measure performance, will start to level out. I don't know if it would level out right at 16 and 17, and that the reason for this, well, for this particular case, the concurrency is in fact more compute bound than it is I/O bound, because we've already read the page in, and now we're counting stuff in memory. So in that case, we probably won't see much more beyond the number of cores. As soon as you start adding more threads than cores, and the work that's being done is compute bound, then when preemptive scheduling kicks in, you're really just slowing yourself down as opposed to making any performance gain. Yeah. Okay. So now let's enter into Alice in Wonderland territory. I don't know how comfortable you are with Lisp, but I always feel like my brain is being bended in weird ways when I encounter it. But this book, its goal is to introduce new models of concurrency and new ways of expressing those models. And so we're going to be learning at least 2 new languages this semester. One is concurrency, one is Clojure, and the other is Elixir. And Elixir has another very interesting concurrency model associated with it. So those will be 2 new languages there. We might even see some Scala at some point, so get ready. Lots of new languages being thrown at you. So I spend the first part of this new lecture just kind of introducing Clojure, which is what our book does. So let's do that right now. So this is going to be from Chapter 3 of our concurrency textbook. This particular set of slides goes through all of day 1 and into the start of day 2. And then we will go a little bit further in this chapter. We'll get through to Chapter 4 a little bit in the next lecture, if we're lucky. And then I'll have to delay the rest of it till after the midterm. We'll switch over to doing, looking at the Agile material, Agile Life Cycles material, as opposed to the concurrency. So yes, so this language that we need to learn at least a little bit is called Clojure. This is their cool little logo, and they have a funny little way of doing the J in their name. To work with this material, you're going to need to install Clojure. Fortunately, it's pretty simple to do, especially if you already, for running the book source code, if you've already installed Maven, then installing Clojure is a snap, because we use this system called Lineagen, and Lineagen uses Maven in the background to download everything that it needs. So on macOS 10, if you have Homebrew installed, you can just say brew install Lanigan. Otherwise, it's actually very simple. I had to do this for Ubuntu earlier this week. You go to lanigan.org. There's just a single script that you download. You make that script executable, put it in your bin directory, make sure it's in your path, type line, hit return, and it will detect that it's being run for the first time and download itself first, downloads the Lanigan code, and then it will start downloading Clojure and all the rest of it for you. So pretty simple way to bootstrap, and this use of Maven in the background has it basically piggybacking off the work of what the Java community did to make it simple for people to get started with Clojure. There is another great way to learn Clojure, and that is through the support that a text editor called Lighttable offers for Clojure support. And Lighttable is available at lighttable.com. This is actually an interesting history to this editor. It was actually created, I think, via a Kickstarter effort from developers that wanted to take a new approach to integrating code and runtime. So it has the ability to put your cursor next to an expression or statement, hit Command Return, and have values show up inline showing you what this code would do at runtime. And that's what its Clojure support allows. So once you've downloaded this Lighttable and launch it, you'll see this screen, as I have it running here. And if you do Control Space as the key binding and type REPL, you'll see here open a Clojure InstaREPL is one of the options. And if you just click on that, up pops a window, which is, it's down here, it's saying connecting. It has to download a few things just to make sure it's got everything it needs. Once it comes back, now you've got a live REPL. So hope you can see that. I don't know if this will, oh good. That makes it bigger. So yeah, so this is now a live REPL, which stands for read eval print loop. And so Lisp, you always put the operators first, then your arguments, that, and it evaluates it instantly and tells you what the answer is right next to it. So you can say map and plus, or here, plus 1%. I'm jumping ahead of myself here, but just to show you. 1, 2, 3, 4, 5. Gotta get the syntax right. And there was a call to the map function. It took an array of 1, 2, 3, 4, 5. It had a function which adds 1 to anything that gets passed to it. So the output here is 2, 3, 4, 5, 6. So you instantly get a kind of an environment in which you can play around. Old expressions can hang around. You can add stuff that builds on this and watch it run. And it tells you that you're live, that you're connected to a REPL system in the back. Otherwise, if you don't want to do Lighttable, once you've got Lanigan installed, let me go back to my own machine. Actually, let's go, go here. And let me open up a new one here. Zoom in so you can see. Just do a temp directory here. The easiest way to get started in Lanigan is like the Rails command for Ruby on is it the Rails command? Yeah, the Rails command for Ruby on Rails. You can ask Lanigan to create a new project for you. So if you say line new, try this, or let's do try this out. It creates a directory called try this out. And it has a basic structure that allows you to have your source code in one directory and your tests in another directory. It made sure that there was a test case that fails. So if you run line test, it'll run and tell you, oh, this test here that's called fail in a test with a documentation that says fix me, I fail. And here it was trying to compare if 0 was equal to 1. So it sets up a little mini environment that you can start using right away. Once you've got one of these directories, or even without one of these directories, you can just type line REPL. And that brings up your read eval print loop. And then the same things we saw in Lighttable can be done just by entering and hitting return. I'll go back to Lighttable here and copy this. Paste it here. we'll see our thing like that. And so here you just enter the expression, hit return, see the value. All right, so that's something, it doesn't take very long to get to the point where you've got one of these REPLs running, and then as you're going through the book, you can cut and paste things in and make sure that you're understanding. And then I realized that learning a new language is non-trivial. There's lots of great resources out there. O'Reilly just came out with a book just last month called Living Clojure, which it's designed specifically to teach people who don't know anything about Clojure from the ground up. And then there's a free download on the Pragmatic Programmer's website called Clojure Distilled, where it's another intro to Clojure. Then there's some books there, Programming Clojure, Applied Clojure. The Applied Clojure is actually a very advanced book. I realize I should probably have taken it off. And then you can go to the website itself, clojure.org, and that website itself has its own cheat sheet on syntax and method names and other things that can get you started. Okay, and then I already talked about this, and I'm going to skip over in the instance of time, in the interest of time, this kind of intro to the Leiningen project structure. There's some interesting information here, but you can review it yourself and then ask me questions if you need to. I'll skip all this and get to the intro of the language. Okay, so why a new language? This language was first developed by Rich Hickey in 2007. It is a dialect of Lisp, as you saw. I was creating parentheses and wrapping expressions with parentheses. However, what was new at the time was that it was built on top of the Java virtual machine. So you installed Clojure by installing first Java and then Clojure on top of it. And now you don't even need to know you're installing Java. You could just download Leiningen script, and it uses Maven in the background to download everything you need. And if you don't have Java, it's going to download Java for you. While it is a Lisp, it can make calls, and the other cool thing is that it can make calls into the Java standard libraries. So no need to rewrite a I.O. package. You can just use java.io already, or Java new I.O., or anything like that. So oftentimes, if you see questions online where you say, how do you do X in Clojure, it's answered by, oh, well, there's this package in Java, you just call that. And so there's a way for you to call Java code in Clojure. There's also a way for Java code to call Clojure code. They made all of that happen via the magic of the Java virtual machine being underneath. So when all is said and done, your Clojure code is being downloaded to .class files, just like Java source code files are converted to .class files before being executed. Clojure's design adopts, but at that point, all similarities end. And you can see this if you go and look up Rich Hickey on YouTube. He's got some great videos in there where he talks about the design of the language, talks about doing concurrent programming, and is pretty opinionated, right? So it's easy, as I say, easy find videos of him casting aspersions on concurrent programming with shared mutable state. So I had that one lecture slide with the one author saying shared mutable state is pure evil. He's definitely in that camp. And so he basically no shared variables, no mutable state. Everything should be immutable. And your concurrent programs should be straightforward. Not easy, but straightforward to reason about. So we're going to start getting a taste of this. Now, one thing that people will say as an initial reaction with this notion of immutable values is like, okay, well, that's all well and good for a variable called a, and it equals 5. I get that if you need to go a equals 6, you don't store the value in a, you create a new version of 5, and you create a 6, and you rebind it to some other symbol. But what are you going to do with like big, complicated tree structures or huge hash tables? These really big data structures. And you're going to tell me that if I've got 3 gigabytes, well, let's be reasonable. Let's say you have 150 megabytes of information in a hash table. You tell me that if I'm going to add a new key to that hash table, I got to create a whole new copy, all 150 megabytes of memory being copied into a whole new hash table just so I can stick one new element in there. And Rich Hickey would say, no, that's crazy. We would never do that. And so actually what happens is that they have figured out a way by using a data structure known as the TRIE data structure, T-R-I-E. If you take data structures at the upper division level, you will encounter tries. And they basically, I forget what it is, but I think it's a TRIE branching factor of like 256. by default, and you can put 1 million entries into this data structure, and it goes down about 4 or 5 levels. And so then to get to any one entry in your data structure takes at most 5 memory reads to get to the bottom of the tree data structure. And then what they do on top is if you want a hash table, they implement the hash table using a trie. You want a linked list, we'll implement it using a trie. And if you want some other data structure for all the common data structures, sets and all that stuff, they're all implemented underneath as these trie data structures. And then what's great about it is if you've got a big 150 megabyte hash table and you want to add a new value to it, the trie reuses everything except what was changed. So they have a way of inserting a new entry that says, here's the new entry in the map, the hash table. This old entry should no longer be visible. Everything else stays the same. And so what you get is 150 megabytes of memory, which then has a small insertion added to it for the new value. But in your program, you actually have 2 conceptually distinct hash tables. Both will never change on you. Right? So one thread could be reading one hash table, the other thread could be reading the other one. And from that standpoint, if they never switch the values, those things are immutable. They never change. So lots of cool stuff is going on underneath to make it so that you can do programming with immutable values and make it easy to reason about concurrency without having to worry about these big memory copies, which if in a naive implementation you would, and it'd bring everything down to a crawl. So let's just set aside those worries. We can take huge data structures that can fill up memory and make changes to them where we have conceptually distinct copies, and underneath it's sharing everything it needs to try to reduce the pain in this approach. Okay, so what we're going to do here is focus more on functional programming style and the way that concurrency creeps into it than we are going to be looking at explicit concurrency constructs of Clojure. And then on Thursday, I'll switch over and talk more about that. So there's things that Clojure offers that are unique to it called atoms, agents, refs. This persistent data structure, I just kind of gave you an overview of what that is, and something called software transactional memory, which allows you to do coordinated updates in the presence of threads, which we'll talk about next time. But this type is more about, if you're just taking a functional programming language approach, how does that help you in designing concurrent systems? So now just a little bit of boot up on Clojure. It's got all your basic sets of data types, booleans, characters, strings, the no value, which is nil, numbers, both integers and decimals, keywords. Here you can think of these things as being immutable strings, but they act as, you can think of them as singleton strings. So if I ever say :first, anywhere in my program, if I reference :first, I'm referencing the same object. That's one way to think about it. But they're used, as you can see, primarily as keys for maps. So over here on maps, :first, Ken, :last, Anderson. So they are typically almost always used as keys into map data structures. You can have symbols. These are our variables. You can think of them as, well, as quote variables, although everything's immutable, so it doesn't vary. But these are the ways we name values that we're currently pointing at. And it does auto mapping of stuff from Java, so Java lang string becomes a symbol that you can reference and do things with if needed be. A list data structure is just a sequence of elements that are surrounded by parentheses. And the closely associated but not as important data structure vector is the same thing but with square brackets. And the big difference between these two things is how they're implemented underneath. In one case, you get fast random access. That's with vectors. You can jump into any point and modify if you need to, creating a new instance. Or with lists, it's fastest if you're only pushing stuff onto the front and taking stuff off of the front. And so it's a particular type of linked list which has different performance characteristics underneath. Now, all programs are written as lists. So every Lisp program starts with an open paren and goes from there. So in fact, the whole data structure, the whole program itself is data. List data structure, and then it has special properties that allows you to then execute that data. Sets are just notated like this and then have the uniqueness characteristic. You can't create a set with multiple things, so I couldn't say 1, 2, 3, 3 there. That would cause an error. But if I had 1, 2, 3 and then tried to add 3 to it, it would keep it unique. and then our map data structure. Now, I don't have any commas in our data structures here, and I don't do like open paren 1, comma, 2, comma, 3, comma. I don't do that, and that is because in Clojure, commas are white space. So we think of new lines, tab characters, and space as white space in programs. Clojure adds commas, which means you can put commas anywhere you want. Doesn't have any impact on your program. They're just stripped out. But if you want, for instance, your map data structure to say colon first Ken, comma, colon last Anderson, you can do that. Clojure won't care. Okay, so to make things happen, you need to have lists in which the first element of the list refers to a function. And when you have such a list, then when you type it and hit return, as you saw earlier, it tries to evaluate the expression by calling that function with the remaining arguments. So this call here, +1, 2, calls the plus function and passes 2 arguments in, 1 and 2, and we get back 3. Plus is a very versatile function, as we'll see later. If you give it no argument, it returns with 0, which is its identity value. You can give it a bunch of arguments, and it will add all of them up efficiently behind. You can give it 1 argument, and it'll just return that value, having added that argument to 0. Times multiply the asterisk symbol functions the same way. Here's a sort function. We give it a vector. We call sort, and it returns a list with the elements sorted. Functions are defined in general using another function called define function, or defn. And defn here takes a name, which becomes the function name, a vector, which contains the number of arguments that we expect, and then forms is just a generic term for all of these types of expressions. So that's where you would start to say, first do this, then do this, then do this. And so the value of the last form in forms plus, so forms plus, that's a kind of a regular expression thing there that says, so this means 0 or more arguments can go in the vector, and 1 or more forms occur here. And the last form will return a value, should return a value, and whatever value it returns is the return value for the whole function call. So there's no explicit return function or return keyword. It's just whatever the last thing evaluated is, that becomes the return value for the whole expression. You can create anonymous functions. I was showing one being used earlier down here. This is the anonymous function syntax. So rather than saying defn and then a name, you just say fn. And then you give it its arguments, and you give it its forms, and it's a function that can be invoked. And what you'll see this being used is in other calls, other functions, which take functions as arguments. And this is where we get into what functional programming is all about. In functional programming, functions are first-class citizens. I can say, here's my variable a, or my symbol a. If I want to use Clojure's terms, I have symbol a, and it points at function foo. And now that it's pointing at function foo, I could call a, and it would be like calling foo. But if a is another function, and it takes 3 parameters, and each of those parameters can be functions, I could be passing functions in to a call of that function. And I can either be passing that function by name or by symbol, or I could be creating the function on the fly. And that's where these anonymous functions come into place. Here I am going to be creating this function, and right now all I'm doing is calling it. Sorry, no, I'm just defining it there. But in other contexts, these things typically get either defined and then passed to other functions, which call them later, or they get defined and immediately invoked, is another way that you can see this happen. And then this is just a short form. This here is just basically syntactic sugar using something that Clojure calls macros, which we will not get into because macros are really complex. Here is another way of specifying an anonymous function where you just refer to arguments via numbers if you need them. So here I'm defining an anonymous function, which the first thing it's going to do is call plus, and it's going to pass 10 into plus, but then it's expecting 2 other parameters, which I refer to as %0 and %1, and those will get passed to plus as well. So to make this a little bit more understandable, if I, oh wait, go here. Yeah, so here, if I copy this and go over to light table, and I change this map function here to now contain that anonymous function here, what I'm doing is that map is one of those functions that expects one of its parameters to be a function. It takes that function, applies it to each element of the vector that comes in next. And so here what I do is I've got an anonymous function. It's going to take a parameter called x, and it's going to add 10 to it. All right? And then here we get back our output values, and it's 11, 12, 13, 14, and 15. We added 10 to it. And then all that happens is this is the same function, add 10 to my input. It's just using the shorthand syntax. So if I go here and swap this out, push play, or just enter, it comes back and immediately executes again. But this defined the same thing, a single function that takes one argument, in this case referred to by the percent sign, and adds 10 to it. Everyone still with me?
For the output?
Yeah, this one I don't know. This is some special feature of Light Table. I don't know what that 5 is. I'm just starting out as a Light Table user myself. But the final output is over here at the very end.
If you change one, if you deleted an element, would it reduce the 4?
Yeah, so not sure what the 5 is, unfortunately. I don't know. Yeah, I could guess, but I think I'd be wrong at this point. Okay, so symbols, if you need a symbol, you can define them using def. Not def-n, that defines functions, but def. So here I'm defining a symbol called pi. Here I'm defining a symbol called x. And these would add pi and x to the current namespace of the REPL or the program, and then they could be referred to directly in your system. So here I can say plus x10, and in this case, since x was 10, I'd get back 20. And then all this does is reference the value of x. It doesn't change x in any way. It's just creating a new value, in this case 20. If you want, you can run the def command again. And that's because the def command is doing what they call symbol binding. It's not like in Scala, where if you say val x equals 10, that creates an immutable variable. And then in Scala, if you say x equals 20, it'll say fail, you'll throw an exception because you're trying to change an immutable variable. Here, it's just saying, hey, the symbol x, I need it to point at another thing that's immutable. And so you're just rebinding what x points at in this case. All right, and then there's typical control flow. Here's an if statement. You give it a function which will evaluate either to true or false. If it's true, it's going to evaluate the first expression. And if it's false, it's going to evaluate the second expression.
Quick question.
Yes?
When you're rebinding, essentially you're losing the original, correct?
You
have something else bound to it as well?
yes, you'd be losing the original, correct. All right, and we got something, wasn't happy about this. We got, don't know. Let's try this here. Sometimes when I copy and paste quotes in, it gets unhappy because of it thinks of them as curly quotes or something. Let's see if that makes it any happier. Oh, I know why. It's because x wasn't defined. x10. There we go. So x is now non-negative. If I said -5, it's negative. Right? So then down here, we can also do what's called the condition statement. And the condition statement here, let me just format it for us humans. The condition statement starts by looking at each expression. The expressions here in each form, the form is 2 expressions each. If the first expression evaluates to true, it evaluates and returns the second expression. So right now, x is less than -5, so it's evaluating and returning small. If x is, here I have, so there's no way to get it to say uh-oh. If I change x's definition to be 100, then that condition will update and say large or medium. Okay, so basic control flow is being demonstrated there.
What if you give it a string or something like that?
If I say, if I said this was quote 10, Yeah, string cannot be cast to integer. So we're getting a problem with how we're actually trying to compare this now. But yeah, that's exactly what these environments are for. Just try it and see what happens. Okay, so now loops are a special case. The reason why they're a special case is that you will typically not code loops explicitly yourself. You'll use something like map or filter or reduce to do the loops for you in a functional way. If you are going to do loops, you will typically not write them as we would expect in an imperative language. You would use recursion. And we'll show that coming up here. All right, so but they do have a loop statement. If you want to do it, you can use it. Basically what you do is you have an open paren loop. Then you have a vector of bindings, and all this means is this symbol equals this symbol equals this symbol equals that, just a way to set up a set of local variables. And then you have a bunch of expressions that need to be run. The call to loop then creates a jump point that allows control to return to the top of the loop by calling another function called recur. And with recur, what you do is you put a set of expressions which rebind the symbols that were defined in the bindings, and the next time through the loop, you get those newly bound values as opposed to the original values. And I'll show you that as an example. So here's a set of Lisp code that says we're creating a loop. We're binding two symbols, result and x. Result is an empty vector, and x is 5. Now we have our first expression says if x is 0, so it's just a way of saying is x equal to 0. If it is, we're going to return result, which is starting out as an empty vector, but as you'll see down here we do some magic to make result happen in a different way. So if it's not equal to 0, then what we're going to do is recur. So this means jump back to the loop. But we have new bindings, and the new bindings are that x needs to be decremented. That's all that dec means. So if x is 5, calling dec x will return 4, and then 3, and then 2. And then over here, conj is a way to add new things to a vector. So we start with an empty vector, and we're going to put the value 5 on it. We recur, and now x is 4, and the vector has a 4 in it. And then we go through, and we'll slowly but surely add 4, 3, 2, 1 to the vector, and then we jump out when we hit 0 and return the result. So if we see this in light table here, let me just clear everything out. Paste. That. We see that it's indeed producing 5, 4, 3, 2, 1. And we can start to experiment. We could say, okay, what is this conj thing? So result starts out as a empty vector. And we know that the first value for x is 5. So it's going to be executing conj empty vector 5. And so sure enough, what it's doing is taking the 5 and putting it into the vector. Then we jump back to the top of the loop. And now we're calling loop where we have a vector that has the value 5 in it. And then over here we have this dec x. So what does dec x do? Or let's do 5 here. It's going to return 4. So when we flip back up to the loop, our new input is a vector which has a 5 in it and a 4. And now it's going to come in, and we're going to get this, 5 and 4. And that produces a vector 5, 4. The next time through, this will have 5 and 4 in it, and this will be 3, and so on. Okay? So Clojure code looks scary until you start to break it down like this into a REPL, and suddenly things will start to snap into place. Now I'm showing you this only to then tell you that you almost will never code your own loops, but it's there if you need to. So you can, now that you've learned about loop and recur, the next thing you should know is that when you do a def n and a function name, countdown, that actually creates a jump back point for you. So if you want this function to be recursive, rather than explicitly calling, in this case, countdown, you can just say recur. And since there's no loop statement, it's going to jump back to the beginning of the function and call the function again. And so this does exactly the same thing that we just saw. It creates this 5, 4, 3, 2, 1. In this case, it's just using the fact that you can jump back to the start of a function using recur. And then finally, you don't need to do any of that recursive stuff because Clojure already has functions like this here. We can say into. Into takes a collection in its second argument and takes all of its elements and puts it into the collection of the first element. So in this case, we're saying take 5 from an interesting sequence here. We'll take a look at that in just a minute. Take 5 of those things and stick it into this collection. And all of these things here produce the same result, 5, 4, 3, 2, 1. In the interest of time, I've got only 5 minutes left to get through this introduction. Let me skip that, but take these expressions here and pull them apart in a REPL and understand what they do. But they all end up with the exact same result. And then finally with map, map as we saw earlier is a function, map here, which takes a function as its first argument. In this case, we're passing it the predefined function inc, which just stands for increment. And we're passing it a range of numbers from 0 to 10. And so the result is a list from 1 to 10 because it added 1 to every single number in the input array. And then you can also do reduce. Reduce takes a collection and an operation. And what it does is it takes that collection and pairwise reduces or combines the values in that collection to typically some single value. So in this case, the plus sign is going to say take the first 2 elements of the collection and add them. Now take that addition and take the next element of the collection, add those together, take the next one, until we add it up. So here, range 10 creates the numbers 0 through 9. The map inc statement creates this array, 1 through 10. And then reduce is going to take 1 plus 2 and get 3. 3 plus 3 is 6. 6 plus 4 is 10. And so on up to 55. So who's completely lost? Anyone? I was completely lost the first time I read it, so put your hands up. It's totally okay. We'll take this slowly, but what you need to do is to get this into a REPL and print some of these things out. So what I would recommend, for instance, is like this statement with the reduce. You go into a REPL or to light table, print it, and sure enough, you get back your 55. But you can do things like this, range 10. What's that do? Oh, 0, and it shows you 0 through 9. And then, I've got to do map and inc and range 10. And that gives me 1 through 10. And then finally, I've got my reduce call. Reduce plus 1, 2, 3, 4. We'll just do it like that. And Java long cannot be cast. I don't know what's going on there. Anyway, let me just do that in the REPL.
Should it be an array? Should it be in square brackets?
Let's see, there and there. Boom. Oh, it should be a function, but plus is a function.
I mean, shouldn't you use square brackets?
Oh, do I have to use, there we go. Thank you. So I have to pass in a vector, not a list.
Is that because with a list it's only good for taking the first element and the...
Well, what I think was happening, I probably can do this if I do what's called an escape. Yeah. So what's happening is I am passing in a list, and the Lisp interpreter says, oh, it's a list. Look at the first thing, and that needs to be a function, and now call that function with the arguments. And what was happening there was 1 is not a function. And so I was trying to call 1, and it's saying, hey, I can't convert a long into a function. That's what was going on there. But by putting this in here, I'm saying, hey, this is just a data structure. It's not a function call. And so don't treat it as a function call. Treat it as a data structure, and now reduce, and now it works. OK, sorry about that. All right, we'll pick up here on Thursday. More to learn. But please, before Thursday, try to get Lineagen installed and play around with some of these forms.